When a reaction is at equilibrium and the forward rate is equal to the reverse rate, and the concentration of the reactants and the concentrations of the products are no longer changing, we can write an equilibrium constant for that reaction. The equilibrium constant is the concentration of the products divided by the concentration of the reactants. So if we have an equation such as this, we have A reacts with B, and it forms C and D. The small letters here are the coefficients, so we would have like 2A and 4B. The equilibrium constant is going to be equal to the products, which are C, and the little c will be a superscript, and D to the D, it's actually a power, the D power. And divide that by A to the 8th power, and B to the B power. So let's see how we do this with a real equation. I'm going to move this down a little, give myself some space. The equilibrium constant for this will be equal to the products, which is the NH3, the ammonia, and they've got two of them here, so we'll have to put the concentration of ammonia squared. Then we need to put the reactants on the bottom. We'll put the nitrogen, and we'll put the hydrogen. The hydrogen we've got 3 of, so we're going to cube its concentration. Do the next one. The concentration is going to be equal to nitrogen dioxide, and we're going to square that, divided by the reactants, nitrogen oxide squared times oxygen. So now we can write these same reactions but put numbers with them. So what is the numerical value for the equilibrium constant for the following reaction if the equilibrium mixture contains, so we've got N2O4, and that concentration is equal to 0.030 molar, and we have NO2, and that concentration is equal to 0.21 molar. Well, let's look at our equation down below here and write our equilibrium constant. The equilibrium constant is going to be equal to the products, it's the concentration of the NO2 squared, divided by the N2O4. That's our reactant. The square comes from right here. And now we can just substitute in. The NO2 is 0.21, and we're going to square it. I'm going to divide it by 0.030. And if we do our math here, we should get 1.5 as our equilibrium constant. what is the value for the equilibrium constant for the following reaction if the equilibrium mixture contains, and then we've got all these things, we're going to write them out. This is our reaction down here. So this is there's a misspelling here. This is supposed to be this is the carbon monoxide in moles. Okay, so we've got 0.51 moles of carbon monoxide. Sorry for the misprint. Hydrogen, we've got 0.30 molar. For methane, we've got 1.8 molar. And for water, we have 2.0 molar. So our equilibrium constant is going to be equal to the products, which are it's going to be the methane and the water. We don't have any coefficients in front, so we can just leave those as ones. And then we've got the carbon monoxide concentration, and then we've got the hydrogen concentration, and this needs to be cubed because of that 3 right there. So now we can fill in the CH4 or methane is 1.8. The water is 2.0. You can divide that by the carbon monoxide. That looks like copper, but it's supposed to be carbon monoxide. 0.51. And our hydrogen concentration of 0.3, and we're going to cube that. If we do the math on this, we'll get 281. Now, when you do reactions like this, it's very important that you make sure when you put it in your calculator that you put your 1.8 multiply by 2.0, divide by the 5.51, and then divide by the 0.3 cubed. Frequently people will not will not divide by that second term. So we can also use our equilibrium constants because we know that equilibrium constant is equal to the products over the reactants. We know that if the equilibrium constant is a large number, we'll have lots of product. And a small amount of the reactants. So for example, if your product is 100 and your reactant you only have 1, that gives you a large equilibrium constant. If the equilibrium constant is small, you'll have a small amount of your product and a large amount, or lots, of your reactant. So you'd end up with the product having something like a 1 and the reactant being 100, you'd end up with 0.01, something less than 1. If they're the same, then the equilibrium constant is going to be equal to 1. You'd have 100 over 100, give you 1. So if it's a large number, we make lots of product. If it's a small number, we make lots of the reactant. So let's see how we can use this in problems. So the equilibrium constant for this reaction is 54. If the equilibrium mixture contains this much iodine and this much hydrogen iodide, what's the molar concentration of the hydrogen? So what I'm going to do is first write down what I know. And I know what the equilibrium constant is. It's 54. And I know that the iodine concentration is going to be 0.015 molar, and that the hydrogen iodide concentration is equal to 0.030 molar, and that we don't know what the hydrogen concentration is. That's what we would like to find out. Well, I can take my equation over here and I can write my equilibrium constant. The equilibrium constant is going to be equal to the product, and in this case it's going to be squared, divided by hydrogen ion concentration times the iodine concentration. And if we look at this, I know this number, and I know this number, and I know this number. So the only number I don't know is this hydrogen ion concentration. So I have an equation with only one unknown. So I'm going to take this and I'm going to multiply both sides by hydrogen. And that's going to get my hydrogen out of the bottom here. I'll be able to cancel it on this side, and then I've got the hydrogen concentration times the chemical equilibrium will be equal to the hydrogen iodine concentration divided by the iodine concentration, and that was supposed to be squared. Don't want to leave that out. Okay. Now I want to get rid of the chemical equilibrium on this side, so I'm going to divide both sides by the chemical equilibrium. And it cancels on this side. And so now we've got the hydrogen concentration is equal to the hydrogen iodide squared divided by the iodine divided by the chemical equilibrium. Okay, so we can just substitute in. We've got 0.030 squared for our top. In the bottom, we have the iodine concentration and the chemical equilibrium. If we do all that math, we end up with a hydrogen ion concentration of 1.1 times 10 to the minus third molar.